Hello everyone, I'm Takumi Suzuki from Ibaraki University, Japan. Today, I would like to talk about integrated converter utilizing tapped inductor with arbitrary voltage step-up ratio to enhance energy yield for curved solar roofs of PHEVs. In recent years, plug-in hybrid electric vehicles with a solar roof, which is a photovoltaic panels mounted on a PHEV's roof, have been developed and commercialized by various automobile manufacturers. However, the curved surface of the solar roof triggers a significant reduction in power generation, and when we use this power, the panel voltage is needed to boost to a desired load voltage. In this presentation, I will propose a novel integrated converter utilizing a tapped inductor with arbitrary voltage step-up ratio, and this proposed converter can enhance power yield from panels. From the experimental results, extractable maximum power improved by 12.3%. This slide shows the outline of this presentation. Firstly, I will explain about the background. Secondly, I will explain a detail about proposed converter. Next, I will show the experimental results using 200 watt prototype. Finally, I will summarize this presentation. Background. At this slide, I will describe the characteristics and issues of curved solar roof. In recent years, PHEVs equipped with solar roof have been developed. The lower left-hand figure shows the configuration of solar roofs. To get a maximum power from curved solar roof, it is composed of 56 cells, and these 56 cells are divided into 7 substrings. Please look top panel of the right-hand figure. The curved surface of the solar roof makes its irradiation levels uneven. As a result, substring characteristics are always mismatched. This is a big problem for curved solar roof of PHEVs. This slide shows the negative influences of characteristic mismatch. 3 substrings connected in series are shown as an example in this slide. Because of the decrement of irradiation levels, the power yield from one substring decreases compared with other 2 substrings. The figure in the center of this slide shows substring characteristics. Horizontal axis is voltage, and vertical axis is current. Red dotted line shows weak substring with low irradiance. On the other hand, black line shows normal substrings. As you can see from this figure, weak substring is likely bypassed at a certain current value. Since the bypass substring no longer contributes to power generation, it triggers a significant reduction in power generation from PV panel, as shown in top panel of the right-hand figure. In addition to it, mismatched panel characteristics exhibit multiple maximum power points MPPs, including a global MPP and a local MPP. The occurrence of multiple MPPs confuses and hinders the conventional MPP tracking algorithms because the PV panel might operate at a local MPP that is a suboptimal point, producing less power than a global MPP. Differential power processing (DPP) converters have been proposed as a powerful alternative solution to the characteristic mismatch issues. In this slide, I will explain the principle of the DPP converter using switched capacitor converter. The right-hand figure shows the substring characteristics. In this figure, there is a difference in current value between the weak substring and the normal substrings at the same voltage value. This differential current is supplied to the weak substring by the DPP converter. As a result, all substrings are virtually unified. SCC plays the role of DPP converter without control by switching. If PV1 is weak substring and the others are normal substrings, SCC can directly transfer the power to the PV1 from the other 3 substrings. From these principles, maximum power can be obtained from each substrings. In addition to the DPP converter, a step-up converter is required for PV systems in PHEV application. A step-up converter not only for boosting the panel voltage to a desired load voltage, but also for tracking the MPP of the panel. However, PV systems are prone to complexity and high cost. To solve these issues, integrated converters have been proposed. Integrated converters realize system simplification and cost reduction by integrating the DPP converter and the step-up converter. Right-hand figure shows the conventional integrated converter based on the SCC and the step-up converter. And the voltage step-up ratio of the conventional integrated converter can be expressed like this. D is a duty cycle of odd-numbered switches, and 7 is the number of substrings. As you can see from this formula, conventional integrated converter is not suitable for PHEV's application, which is composed 7 substrings because of the low voltage step-up ratio. Proposed converter. I will propose a novel integrated converter utilizing the tapped inductor. Proposed converter is based on the SCC and the step-up converter. The SCC and the step-up converter are integrated into a single unit with sharing Q13 and Q14. As a result, the proposed converter realizes system simplifications and cost reduction by reducing 2 switches, compared to the case where the SCC and the step-up converter are used separately. The SCC unifies the substring characteristics without control by switching, as I explained on the previous slide. The step-up converter has boosting operation thanks to magnetizing inductance of the tapped inductor, and the step-up converter can control load voltage by PWM control. Therefore, the output voltage Vout is adjusted by D, or turns ratio of the tapped inductor. This proposed converter can achieve arbitrary voltage step-up ratio thanks to turns ratio of the tapped inductor. The details will be described later. In this slide, I will explain the operation of the proposed converter. The operation analysis is performed of uniform substring characteristics condition thanks to the SCC. The operation modes are divided into 3 modes. However, I will only explain about mode 1 and mode 2 because of the time limit. Left-hand figure shows the theoretical key operation waveforms. These waveforms describe the voltage of switches, the current of magnetizing inductance, the current of leakage inductance, and the current of diode. In this mode, the odd number switches are turned on, and the even number switches are turned off respectively. The voltage of magnetizing inductance VLMZ can be expressed as VPV7 minus VC7. VPV7 is the voltage of PV7, and VC7 is the voltage of the capacitor C7. The current of magnetizing inductance ILMZ linearly increases, and the tapped inductor stores energy. The diode does not conduct. Therefore, the current is not supplied to the secondary side of the tapped inductor. In mode 2, the odd numbered switches are turned off, and the even numbered switches are turned on respectively. LMZ and C7 are connected in parallel. Therefore, VLMZ can be represented as minus VC7. ILMZ linearly decreases because the polarity of VLMZ is reversed compared with mode 1. As a result, tapped inductor releases energy. The diode conducts, and the current is supplied to the secondary side of the tapped inductor. The voltage of the secondary side of the tapped inductor is n times as much as the primary ones. The theoretical voltage step-up ratio is obtained from the volt-sec balance on LMZ. By using VLMZ of mode 1 and mode 2, the theoretical voltage step-up ratio can be expressed like this. N is the turns ratio of tapped inductor, and 7 is the number of substrings. Right-hand figure shows the characteristics of voltage step-up ratio. Horizontal axis is duty cycle, and vertical axis is voltage step-up ratio. Red, blue, and black dotted line represent n equals 3, 2, and 1 respectively. And yellow line represents the voltage step-up ratio of conventional integrated converter. According to this figure, the proposed converter can not only achieve arbitrary voltage step-up ratio by adjusting turns ratio of tapped inductor, but also accomplish wide range of voltage step-up ratio compared with conventional one. Consequently, proposed converter is suitable for PHEV's application, which is composed 7 substrings. Experimental results. Left-hand figure shows the photograph of 200-watt prototype for 7 substrings. Right-hand figure shows substring characteristics. An experimental equalization test was performed emulating the mismatched condition. PB1 was emulated, the short circuit current decreased by 15%. Under this condition, an ideal maximum power is 83.84 watts. The MPP voltage was 38 volts from substring characteristics. The output voltage of the panel was assumed the battery of PHEVs, and the output voltage was set to be 48 volts. From these values and aforementioned formula, tapped inductor was designed 6 to 18. These are the result of experiment. Left-hand figure shows PV characteristics. Horizontal axis is panel voltage and vertical axis is power. Red dotted line is without proposed converter. On the other hand, black line is with proposed converter, respectively. As As you can see from this figure, thanks to the proposed converter, local NPP disappeared and extractable maximum power improved by 12.3% and the total efficiency was 97.9%. Right-hand figure shows the characteristics of voltage step-up ratios. Plotted red point is experimental value and black dotted line is theoretical value respectively. From this figure, the boosting function of the proposed converter was confirmed, so proposed converter is suitable for PHEV's application. The difference between experimental and theoretical value is considered that leakage inductance affects the voltage of magnetizing inductance. Conclusion: the curved surface of the solar roof makes its irradiation levels uneven. As a result, it triggers a significant reduction in power generation from PV panel, and the occurrence of multiple NPPs is a big issue. In addition to the DPP converter, a step-up converter is required for PV systems. Therefore, PV systems are prone to complexity and high cost. Proposed integrated converter can not only achieve system simplification and cost reduction, but also achieve the arbitrary voltage step-up ratios by adjusting turn ratio of the tapped inductor. From the experimental result, extractable maximum power improved by 12.3% and the proposed converter effectiveness was experimentally confirmed. Thank you for your attention.